Today we're going to do an introduction to wave optics. When an object is big compared with a wavelength, we use geometric optics. That's what we studied last week. The thickness of this soap bubble is not big. That's why we're seeing these swirly patterns of colors. So our goal for the remainder of the semester actually is to be able to understand what's happening here. Here's another example. Same sort of thing. The structure of the surface of this bird's feathers are also not big compared with the wavelength of the light. Geometric optics ignores that light is a wave. We see that hummingbirds and soap bubbles insist that we don't ignore it. You may have noticed that the red part on this type of hummingbird doesn't always look red. It depends on the direction the sun is going and where you're standing. So you could look at it from the side. Sometimes it doesn't look red at all. So this is something that's characteristic of wave optics, is it's very directional. Okay, so let's remember a little bit about waves. So here we have a wave traveling along. I've put a few things, if you think of it as water, it's a few things floating in the water. So those are holding still horizontally, but they're going up and down with the waves as they pass. Now, mathematically, this is how we write out a traveling wave. There's a number of parts in it. First, we have the amplitude. That's the height from the center of the wave to the peak. And this wave there. And then we have our favorite, a trig function. And it has two parts. It's got a part that depends on where you are, and a part that depends on what time it is. Okay, so it has this same structure for both the spatial part and the temporal part. Okay, we have 2 pi, a scale, which is the wavelength for space, and the period for time. Okay, we know this has to be this way because the wavelength is the distance you have to move to go through a full cycle. So if you take that distance and divide, or if you move that distance and divide by the wavelength, you get 1. And we know that the cosine increases a full cycle when the argument increases by 2 pi. The same goes for the period. So we have these 2 fundamental guys defined, and the speed of the wave is defined by the ratio of the wavelength and the period. You can always remember that one because the units won't let you do anything else. Remember, speed is distance per time. Okay, this is a bit cumbersome to write. So most often we define this number k, not the same k as you've used before. This is called the wave number. So it's just a constant, which is 2 pi divided by the wavelength. And we do the same thing for the frequency. 2 pi over the period. That allows us to write out our traveling wave like this. So we don't have the fractions anymore. It's just easier, less mistakes. Now, we normally think about this in a slightly different way. So if we just think about one of these dots here, just take this one, I want this one. It's moving up and down. Okay, so at that point, if we think about this kx, it's going to have a fixed value. So we call that the phase. The reason it's the phase because it tells us where we are in the cycle. Now, if we compare these different red dots, they're all at different places. This guy over here and this guy there. They're not going up and down at the same time. All of them are executing the same type of motion. They just oscillate up and down. But they're not at the peak at the same time. Okay, so the phase is what we use to describe where we are in the cycle, like the phases of the moon. Okay, so each of these has a different phase, and that's what this number here tells us. For this position 2, there's a fixed number there for the phase that says where you are in the cycle at t equals 0. So let's try something a little more complicated. So here we have another wave, which is like 3 point sources. So you can see them here. One here, one there, and one there. Now, this looks really complicated. But I want you to think back to this graph here. Each point is just oscillating up and down. And an oscillation really only has 2 free parameters. You have the phase and the amplitude. They're all oscillating with the same rate because they're being driven by the same frequency. So if we think about this general case here, suppose we take some particular spot we're interested in right here. Maybe a little farther over. So you see right now it's yellow, that's high. Now it's in between green, now it's blue, so it's down. Now it's green again, it's in between. Now it goes back up to yellow. So it's oscillating. Now the amplitude of the oscillation there is different than the spot there. Hopefully that one you can see is a lot smaller amplitude. So this amplitude term is going to depend on where you are. Okay, so these are at different positions. We're using this vector r to describe the position. So there's an r that points here, and there's a different r that points over there. Okay, so each point has a different amplitude of oscillation. They also can have different phases. So the two that I've drawn, one seems to be at a maximum right when the other one's at a minimum. So those have different phases. So also this term depends on the position. But it is still just more or less the same as what we had for that simple traveling wave. Okay, so that's the simple thing about this diagram, but what those functions are could be quite complicated. We have these two functions, and they would describe this field. Okay. If we knew those functions, we also know that we could calculate the intensity. If you remember, the average intensity, the time average intensity just depended on this amplitude, not on the phase at all. It just depends on the amplitude, in fact, the square of that amplitude. Okay, so we have the intensity. Remember this, without the c is the energy density. We multiply by the speed of the wave to get the intensity. Okay, that's the time average intensity. Now, I've also calculated the intensity for this distribution of 3 points. You see it's not changing in time because this is the time average. So it's, in some ways it's simpler than the amplitude of the wave, because it's not changing in time. Okay, so you can see that there's In this graph here, red is large intensity and blue is small intensity. So you can see that there's these bands here corresponding to these guys out here that seem to have low intensity. And this is characteristic of wave phenomena, that you have places where it has high intensity and places where it's low intensity. You might think back to the soap bubble, or why the throat of the hummingbird sometimes looks bright and sometimes it doesn't. Okay, so in general you could have fairly complicated patterns. So maybe we should start with something simpler, and about the simplest thing we have is a point source. So here's our source over here. And if we imagine picking a point out there, and we wanted to know what the electric field was at that point, we would take this distance from the source to that point and just multiply by the wave number to get the phase. So this is nice and simple. It's no longer a vector. R is just the distance from the center. It's not a general vector. It's very specific now. So that allows us to write out the whole wave. This function depends on what kind of space you're in. So in three-dimensional space, it's proportional to 1 over the distance. If this was flat, or two-dimensional, it'd be 1 over the square root of the distance. If we look at the intensity, the time average intensity, it looks kind of boring. Just that 1 over R intensity. So it just drops off as we move away. Now, the next simplest would be 2-point sources. We know by the superposition principle that the total electric field is just the sum of the two electric fields if you just had them individually. So this could be source A, this could be source B. Now, but it gets much more complicated than it was before. I mean, you can still see this radial pattern here. And likewise, this one for that one. And they seem to cross over. But they just add. If one is up, the other is up, then it's twice as up. So these yellow guys are where both of them are up. You can sort of see they're at the crossing points. I don't know how to freeze this, so I can't. It's kind of yeah, it doesn't freeze for long. Whereas the blue parts, the little blue dots, are where both of the waves are at a trough. Okay, and the green ones are something in between, where you have the peak of one and the trough of the other, and they cancel each other out. Okay, so it's sort of interesting here in this section, because the waves are propagating in opposite directions. So sometimes all of the waves in that frame are going the opposite direction, and sometimes they're going in the same direction. So it goes really high, and then it flattens out. Perhaps you'd seen something like this if you've been out in a boat and you cross paths with another boat. When the wakes cross over, you get this sort of washboard pattern. Okay, so we could move on to if we go back here, I've moved the 2-point sources closer together to get a tighter pattern. It's a little easier to graph. So here you can see these bars seem to be staying flat, which is kind of odd. This is easier to see if we look at the intensity. We have those bars again, and then the bright spots in between. This particular one, I've taken the distance between the two sources to be 9/2 of the wavelength. Here it's the same thing, but I've zoomed out. So you can see now the scale here is different. So here it only went up to 10, now we're up to 400. So that other box is way down in there. So we've zoomed way out, and now the pattern looks relatively simple. These are straight lines coming in now. Up above, they're curved. These are hyperbolas, I think. Okay, but when you zoom out, if you're far from the source, now the important thing is that they have to be far compared with the wavelength, but also the distance between the two sources. So in this case, they're so small you can't actually see them anymore. They're crushed into there. They're only 4 apart. And the wavelength is 1. So on the scale, they're just like a dot there in the middle. Okay, so that's your source, is both of those slots. Both of those sources are in that same dot. All right, so in this case, we get this relatively simple result that for two sources, a distance d apart, d is the distance between the sources, k is the wave number. I'm going to set up some coordinates here. So this is perpendicular to the two slits, so that the two sources were this way, very small. So this is a line perpendicular to the line connecting these guys. And the angle, so if I take a point out here, send the line through it from there, this is the angle theta, the angle from the normal. And of course r is this distance here, back to the source. Okay, so the intensity depends on r, the overall intensity, but it's separate from the angular dependence, which is makes it mathematically much easier to deal with. Okay, so this term depends on r, and this term depends on the angle. We're going to see where this comes from eventually, and we'll see some simplifying approximations, which are quite often appropriate, that make this result even simpler. Here's a graph of that function. So what this is if we imagine taking a circle around here at a fixed radius, so that this was a constant, then all that we'd have is the variation in the angle. So this is that variation in the angle. Again, this is in the case where the distance between the sources is 9/2 the wavelength.